Hello and welcome to the second video in our three-part series on tropical jets and disturbances. In this video, we're going to focus on African easterly waves, the primary synoptic scale mode of variability in the lower to middle troposphere across Africa, and one of the key features that gives rise to tropical cyclones in the Atlantic basin and to some extent the eastern North Pacific basin as well. So let's start with this Hofmahler diagram, where Hofmahler again is just a fancy name for a time and space diagram. So we have this in two parts here at left. Time increases going down on the left-hand side over the course of about a 4-day period from the 5th of September through to the 9th of September. And then we pick up on the right-hand side where we pick up on the 9th of September and continue down 4 more days to the 13th of September. So ideally, we'd want to stack the right beneath the left, but unfortunately we're not able to get that there and have it be legible on this type of frame. So we'll take a look at the left-hand side first, and we can start with the formation of one of these African easterly waves manifest through convection, given by the yellow and orange on the infrared satellite image here, over eastern Africa. And this is near the Ethiopian highlands, as well as within the left exit region of the tropical easterly jet that we discussed in our previous video. And this feature ultimately moves to the west, which is downward on the Hofmahler diagram. So in any given picture, west is going to be to the left. But in the case of going forward in time, that would be down. And so a combination of down and to the left gives us westward motion over the course of time progressing. They move about 5 to 8 meters per second, roughly 5 to 8 degrees longitude per day with the easterly trades. So here at the beginning, we're around 20 degrees east, and 8 days, 7.5 days later, we're at about 20 to 25 degrees west. So we've moved roughly 45 degrees latitude over the course of about 8 days of time, which is roughly 5 to 6 meters per second for this particular feature. We see convection in association with this African easterly wave, but it's not persistent over the entirety of this 8-day period, especially early on here on the 6th, 7th, and 8th of September for this particular case. We see periods where it is relatively intense and well organized, and periods where it is not particularly intense or well organized. And then that continues with the next 2 frames, and then the next couple of frames. Through much of the period until the feature emerges off of the coast of Africa in this case. We see that convection is maximized during the local overnight hours. Just like we see over land here in the United States during the day, thunderstorms form in the late evening and then organize into a larger mesoscale convective system during the overnight hours that then dissipates as you move into morning and early afternoon when the atmosphere is at its coolest near to the surface and is beginning to warm up to set the stage for the next day's convection. The same thing holds true over Africa. So in the local overnight hours here, 6 UTC is 6 in the morning roughly over Central Africa. We see a maximum of convection. And most of these maxima of convection are between 0 and 6 UTC until the feature actually emerges off of the coast. Whereas most of the times where convection is relatively weak are roughly around 12 to 18 UTC during the local afternoon hours and into the local early evening hours. So these again are decidedly synoptic scale features. Note the extent of one of these areas of convection, roughly 5 to 10 degrees longitude here, and that's just for the area of deep moist convection. If we look over here on the right-hand side, we have one easterly wave here in the lighter shaded region, but then our next one is back to the east, roughly by 20 to 25 degrees longitude, which is roughly 2,000 to 2,500 kilometers near to the equator. These features repeat every 3 to 5 days and have their greatest intensity during the summer, when you get the strongest heating and strongest lifting along the Ethiopian highlands over eastern Africa. What this diagram shows in this particular case here, this was Helene from 2006, I believe, in the North Atlantic basin, is that this African easterly wave ultimately spawned a tropical depression and then ultimately a tropical storm over the eastern Atlantic basin. Not every African easterly wave ultimately spawns a tropical cyclone over the Atlantic basin, but around half of the tropical cyclones over the Atlantic basin do have origins with African easterly waves. As we'll demonstrate later on in this video, African easterly waves have a distinct vertical structure that has their maximum intensity in the middle troposphere, not near the surface, and a distinct cold anomaly near to the surface relative to areas that surround the wave. For a tropical cyclone to form, we need to get rid of that low-level cold anomaly and bring the strongest part of that disturbance down to the surface to give us a warm chord structure associated with a tropical cyclone. The way that we do that is going to be discussed in later videos and later modules, but keep in mind that the structure that we have here for African easterly waves has to be transformed by some set of physical processes in order for one to give rise to a tropical cyclone, and that doesn't always happen with every single African easterly wave. So we can discuss a little bit about how African easterly waves grow once they've initiated. In the previous slide, we saw this series of active convection, weak convection, active convection, weak convection. And that certainly helps to maintain the African easterly waves. But if we think about it in terms of dynamical forcings, there's a combined barotropic and baroclinic growth mechanism. And I don't expect that you all have heard about either one of those yet, so I'm going to try to give a little bit of a primer on what these two are in a very generic, very much non-mathematical framework here. So what do we have depicted here from our friends over at UW-Madison, their satellite group, is a water vapor satellite loop from a case back in 2009 where there's a deep trough along the east coast of the United States across eastern North America. And we can infer the presence of a jet streak along this corridor of yellows and oranges here, which is relatively dry air in the base of the trough here. Note how this looks like a strip of yellow and orange initially, but late in this loop we see a couple of coherent circular blobs in the form of vortices that have formed along this particular strip in the base of the trough. They have formed through a method known as barotropic instability, the breakdown of a strip of cyclonic rotation or cyclonic vorticity, like we see in the base of a trough, into smaller scale, mesoscale individual vortices, like we see here in the diagram at left, as discussed in a moment ago. This strip of cyclonic vorticity within the base of the trough has its origins to vertical or horizontal wind shear across that. You typically have a maximum of wind speed going around the base of the trough because that's where your height gradient between the area of low pressure off to the north and west in this case, and high pressure off to the south and east is ultimately maximized. From the base of the trough to that area of higher wind speed, you get flow in this particular case that is strong out of the southwest and then weak out of the southwest. So you're going to get something in the wind that is going to rotate in a cyclonic fashion along that strip. So we get a large strip of vorticity, and this barotropic instability causes it to break down into coherent vortices. In the context of African easterly waves, the horizontal wind shear is tied to the African easterly jet, where you have a maximum of easterly flow, and it's less easterly to the north and less easterly to the south. So there's a strip of cyclonic vorticity that's found equatorward of the African easterly jet, where you have the strong easterlies to the north, weak easterlies to the south, and putting a stick in the wind, it's going to rotate in a counterclockwise fashion. So let's take a look back at that African easterly jet structure, and in particular the 600 hectopascal zonal wind with the African easterly jet. So we had before a green arrow that came in through this maximum of easterly flow between 10 and 15 degrees north latitude. Now we want to consider the area where the African easterly waves typically form here in eastern Africa. And in this particular region, let's consider a trek northward. So let's start at the equator, in the equator to 10 north region here. And in this case, the zonal wind starts as a small negative or easterly value of around 3 meters per second. And we cross contours to our maximum easterly value of about minus 10 meters per second near 12 degrees north. If we keep going north from here, over the course of the range from about 12 to around 20 degrees north up to 25 degrees north, we increase from a negative 10 meter per second zonal wind, so a strong easterly wind maximum, to a weak westerly wind maximum of 3 to 4 meters per second here. So putting a stick into the wind in this region would cause for cyclonic rotation equatorward of the jet and anticyclonic rotation north of the jet. And if we keep going further to the north, we only see the zonal wind increase to about 5 meters per second out of the west. So it's a much slower rate of change as you go north along this particular purple corridor from the equator through the jet maximum around 10 to 12 north, and then to the westerlies that are found further to the north from there. So we can take that information to sketch a north-south profile of the 600 hectopascal zonal wind. So the x-axis here in this diagram is the zonal wind. Easterly wind is here on the left, consistent with U being negative in that case. And then westerly here is on the right, consistent with U being positive in that case, flow toward the east and toward the west. Latitude at 0 degrees east or 20 degrees east is depicted here on the vertical axis on this diagram. So the equator is down here at the bottom, and 30 degrees north up toward the Mediterranean Sea is depicted here at the top of the diagram. So we started again at about 3 meters per second from the east, depicted here, and we increase to 10 meters per second from the east around 12 degrees north latitude, and then we quickly decrease to about 3 meters per second westerly here by 20 degrees north latitude, and then we have a much slower rate of increase to 4 or 5 meters per second westerly by the time we reach toward the Mediterranean Sea. So that's how we get this red line that we have depicted here at left. So let's put a stick into the wind and see how it turns. And in this case, we're going to consider 3 regions. We're going to take the jet axis that we see here and consider one region to the south of that. We're going to consider a region just to the north of that where we have this sharp decrease in the zonal wind here. And then we're going to look at a region north of that, closer to the Mediterranean Sea. And we're going to see how that stick in the wind turns. So let's start south of the jet axis. I've added in some blue arrows here to depict the wind at each of these different latitudes. Out of the east in all cases, but the vector is longer as you get toward the jet maximum here. So putting a stick into the wind at this longitude here is going to cause it to rotate in a counterclockwise or cyclonic fashion. Whereas if we go just north of the jet axis, we have this very fast easterly wind that quickly becomes a slow westerly wind over a short range of latitudes. Note the difference between this blue arrow and this blue arrow as compared to the blue arrows before. So putting a stick in the wind here is going to cause it to turn in a clockwise or anticyclonic fashion. And it's going to do so very, very rapidly, as given by the double green arrows that we have here, because of the very large change in the zonal wind with latitude as compared to further to the south. And if we go even further to the north, adding in some blue arrows to depict the westerly flow there, it does increase, so it's going to cause cyclonic rotation, or sorry, anticyclonic rotation there as well, but it's going to be relatively weak in this case. The stick will turn over, but there's not a lot of change in the zonal wind that we see across this region. So it's given here by this relatively thin but green rotation marker that I have depicted here. So in terms of barotropic instability, what we're really interested in is not this particular cyclonic or this particular anticyclonic or this particular anticyclonic rotation, but how does it change as you go from south to north? So if we go from south of the jet axis to north of the jet axis, we go from something cyclonic or positive to something anticyclonic or negative in terms of the sense of that rotation. So we go cyclonic, positive to negative, so we're decreasing. Then, as we go from north of the jet axis to even higher latitude, we go from something that is very strongly negative, anticyclonic rotation or anticyclonic vorticity, to something that is less strongly negative in terms of anticyclonic vorticity. So we actually increase once again. So as we go from south to north across the jet axis, we start by decreasing our rotation in the terms of vorticity, and then we increase that. And it's that change in sign, negative along into the south of the jet axis and positive to the north of the jet axis, that gives rise to barotropic instability. So this cyclonic rotation south of the jet axis here breaks down not from that strip of vorticity, but into coherent disturbances as a result of this barotropic instability actually taking place. And that's what gives rise to the intensification of African easterly waves at the expense of the African easterly jet. But it's not the only mechanism that gives rise to the intensification of African easterly waves. So we have our vertical cross section from our previous video here as well at 0 degrees east, and we're looking from the equator to 30 degrees north latitude, 1,000 to 100 hectopascals on the vertical axis here. If we look at 12 degrees north through the jet axis here, we had low-level westerly winds associated with the West African monsoon and upper-level or mid-tropospheric easterly winds associated with the African easterly jet. So we have a vertical wind shear located here, from westerly winds given by this short green arrow to easterly winds that become stronger with height associated with the longer easterly green arrows. And then that becomes somewhat smaller as you go up a little bit further from there. So there's a vertical wind shear that is associated with this, and this gives rise to our baroclinic instability associated with a vertically wind sheared type of environment. And so the vertical wind shear between the West African monsoon at low levels and the African easterly jet at mid levels gives rise to conditions that favor baroclinic instability that allow the waves to grow at the expense of the jet as well. So the African easterly jet is strongest between African easterly waves, and it's weakest right where you have the African easterly waves located. The waves grow at the expense of the jet. And that's a key point that I want to make here. The waves grow at the expense of the jet, whether that be due to baroclinic or barotropic instability. So that sort of wraps up our discussion of their dynamical growth mechanisms. Now we want to take a look at their basic structure. So we have this idealized schematic here at left, and we have surface isobars in the black dashed contours here, missing the leading 10. So this is 1,010 all the way up to 1,022 hectopascals. And note how they bow toward the north in this case. So at any given place along that bowing structure, the pressure is lower than it is to the west and to the east. So we have an area of low pressure, and then the red contours that we see here are streamlines between 700 and 600 hectopascals. They have a similar bowing shape with even a cyclonic closed one depicted here, but note how those red contours, the bowing region is offset slightly to the east of that within the surface isobars. And we have that depicted by this surface wave axis here in white, and then the wave axis at mid-levels further to the east here also in white. So African easterly waves manifest as inverted troughs. We call them inverted because they bow upward, which in the mid-latitudes we're used to seeing in terms of areas of high pressure, as compared to troughs in the mid-latitudes that bow like this, associated with areas of low pressure. This trough or wave axis tilts rearward. So in this diagram here at left, we have the two wave axes depicted here in the white lines, where the one at mid-levels between 7 and 600 hectopascals is to the east or to the right of that here at the surface. If we do a vertical cross section across this region here, say across Hispaniola toward Puerto Rico, we get this type of diagram that we have here at right, where this black dashed region depicts the wave axis further to the west here near to the surface, and then further to the east as you go up. But note that with the African easterly jet, even extending out into the Atlantic Ocean, we typically have an easterly vertical wind shear. The easterly wind becomes stronger as you go upward with height. And so this wave axis tilts backward toward that stronger wind at higher levels. The African easterly waves are most intense in the middle troposphere near the level of the African easterly jet, which kind of makes sense if we think about the waves growing at the expense of the jet. We know that the jet is strongest at 600 to 700 hectopascals, so it makes sense if the waves too were also strong at the level at which the jet was located. So to wrap up this set of videos, I want to take a step through a series of diagrams that help us depict the structure of African easterly waves. And many of them are going to be depicting the surface, 850, 700, and 200 hectopascals here. They have kind of a weird set of axes here. They're very similar to a longitude and latitude axis, but they're really centered on the wave center at 700 hectopascals type of axis. The y-axis is delta latitude, and 0 is the center of the wave at 700 hectopascals. So this would be 4, 8, and 12 degrees north, 4, 8, and 12 degrees south of the wave axis center. And the wave center in the x-axis here category is at 4 for the 700 hectopascal wave. And so I'll add in the stars here to help orient ourselves in that regard. Every category that we have here is about 3 degrees longitude, or about 300 kilometers. So category 3 and 5 would be 3 degrees longitude west and east of the wave axis center at 700 hectopascals. So we can interpret this like we would a spatial plot at each one of these 4 surfaces. And so in terms of the key features we see here, at the surface, to the north of the 700 hectopascal wave center, we see primarily convergent flow. And then at 850 and 700, we see primarily cyclonic curvature, more evident here at 850 hectopascals, albeit with relatively light winds, given the barbs that we see here, than at 700 hectopascals, but we see stronger winds, especially to the north of the wave center at that altitude as compared to 850. Whereas at 200, we see broad anticyclonic flow with the area of high pressure located further to the north and to the east of these particular features. So we have low-level convergence that gives way to cyclonic rotation at mid-levels, and then divergence and upper-level anticyclonic rotation here at 200 hectopascals. The wave center, noting that this yellow star here is the wave center at 700 hectopascals, note how the wave center at 850 is a little bit to the left or to the west of that here at 700 hectopascals. So just as we saw in our previous diagrams, the wave tilts to the east as you go upward, especially within the lower to middle troposphere. We can quantify that curvature of the field in terms of the rotation or the vorticity field. In the surface 850 and 700 hectopascal charts, the contours that we're looking at here are all positive valued, denoting cyclonic rotation. 0.25 times 10 to the minus 5th inverse seconds here at the surface, 1.5 times 10 to the minus 5 inverse seconds, and 3 times 10 to the minus 5 inverse seconds at 700 hectopascals. So we see cyclonic rotation as you go up from the surface to 850 to 700 hectopascals, and it increases as you go up. And it's around 700 to 600 hectopascals where the wave's cyclonic rotation is strongest, as we alluded to a little bit earlier. But as you get to 200 hectopascals, this changes and actually becomes anticyclonic. So all of these contours that we see near to the wave center at 700 millibars and to the north and to the east from there are negative, depicting clockwise rotation or anticyclonic flow, consistent with what we saw in the wind field before. And for this is the anticyclone that we see in conjunction with the strong heating over the Tibetan Plateau and the Saharan Desert in association with the Asian monsoon and the Saharan heat low, respectively. We can also take a look at the divergence field. Is wind coming together, converging, or diverging at a particular level? And if so, where? So again, noting that the stars are the wave center at 700 hectopascals, we see a C out in front of the wave at the surface in 850, and a D behind the wave at 850 in the surface. This indicates convergence at low levels ahead of the wave and divergence at low levels behind the wave, keeping in mind that the wave is moving from right to left with the easterly trade winds in all of these panels. By the time we get to 700 and especially 200 hectopascals, it flips. We see divergence ahead of the wave axis and convergence behind the wave axis. So that's what these two notes are indicating. Ahead of the wave axis, we have low-level convergence and then mid and upper-level divergence. Behind the wave axis, we have low-level divergence and mid and upper-level convergence. And so if we think about integrating upward from the surface, at ahead of the wave axis, air coming together is going to be forced upward, and then it will diverge out in the mid to upper troposphere. So we would expect to see rising motion ahead of the wave at low to mid levels. And then behind the wave, flow that diverges will have to be replaced from air coming above, and so we would expect to see sinking motion behind the wave axis. And that ultimately is what we do see. We can confirm this by taking a look at cloud and precipitation coverage. Where we have ascent, we would expect to see a greater amount of convection and thus a greater amount of rainfall. And that's exactly what we do see. The convective cloud fraction, how much of the area is covered by thunderstorms, is higher to the west, ahead of the wave, than it is to the east, behind the wave. And the precipitation rate is also higher, 15, 20 to 25 millimeters per day ahead of the wave axis, and less than 10 millimeters per day behind the wave axis. So where we have forcing for ascent, we have our convective cloud, our precipitation, and where we have forcing for descent, we see less in the way of convective activity and less in the way of precipitation. So one last diagram. We're going to take a look at temperature anomaly in the top row and relative humidity anomaly here in the bottom row. The first column is low levels, 850 hectopascals, and the second column is upper levels, 300 hectopascals. And the wave center at 700 millibars is again given by the yellow star. So if we focus on the temperature anomaly field here, the contours that we see here are for a cold anomaly, 1.5 degrees Celsius, 1.5, and 0 degrees Celsius on the negative side. So near the center of the African easterly wave, there's actually a weak cold anomaly at low levels. Whereas here at 300 hectopascals, it's kind of covered up by the star, but this dashed contour indicates a warm anomaly at 300 hectopascals. So it's relatively cold at low levels and relatively warm at upper levels, but both anomalies are relatively small. For a tropical cyclone to form, we do want that warm anomaly aloft, but we want to get rid of that warm anomaly near to the surface. And coincident with that, we don't want the maximum intensity to be at mid-levels. We want it to be right there just above the surface, just above the frictional layer. And so we have to see a transformation from this temperature anomaly structure at low levels that we have with the easterly wave to one that has a weak warm anomaly at low levels. And again, we'll talk about what that looks like as we get to a future video. In terms of relative humidity, it's relatively dry. We see this D here with minus 10% contour ahead of the wave and relatively moist with 15% contour here behind the wave. And the pattern flips and shifts a little bit to the south as you get to 300 hectopascals. Slightly moist, 10% or so ahead of the wave, and slightly dry, 10% or so behind the wave. And we can interpret this primarily as the precipitation that's out ahead of the wave, helping to moisten the upper troposphere compared to what you would see in the absence of convection, where sinking motion helps to dry it out. So that's what we can see from the relative humidity anomaly here. So summarizing all of what we've talked about here, our African easterly waves form over eastern Africa and then propagate with the easterly trades. They're decidedly synoptic scale features. Every several days, you get a new wave. They last on the order of a week, perhaps a little bit more, especially if they can form into a tropical cyclone. And their horizontal scale is 1,500 to 2,500 kilometers in extent, so very much on the synoptic scale. We talked about how they grow in the context of this barotropic and baroclinic instability. Both of them extract energy from the African easterly jet and feed it into the coherent cyclonic disturbance that we know as the African easterly wave. So the jet weakens as the wave strengthens, and vice versa. When there's not a wave present, the jet is relatively strong. Then finally, we saw and demonstrated that the waves are strongest at mid-levels with a low-level cool anomaly below them. We need to change both of those characteristics to allow for a tropical cyclone to form, and that'll be one of the subjects for most of our lectures in the rest of the semester. But for now, we end here for African easterly waves. Our last video in this series will cover the Saharan air layer, one more feature of the meteorology of the tropical African continent that also has some connection to tropical cyclones over the North Atlantic basin. So until then, thanks for tuning in.